Hello. Hello. Ah. Okay. Hello. నువ్వు
స్టార్ట్ చేద్దామా? హలో
మాస్టర్ ఒక్క నిమిషం జస్ట్ ఓకే మీరు ఇది స్టార్ట్ చేయండి నేను ఇది మాట్లాడతాను ఫోన్ లో
మీరు మీ స్క్రీన్ షేర్ చేసి నాకు
College of Engineering Karnataka.
యా నా స్క్రీన్ కనిపిస్తుందా?
ఇంతకుముందు వచ్చింది కలిపి మళ్ళీ పోయింది. ఇప్పుడు వస్తుంది.
యా
फ्यूचर सिक्योर कर लो.
ఇప్పుడు చూడు కనిపిస్తుందా?
కనిపిస్తుంది కనిపిస్తుంది.
ఓకే గుడ్. స్టార్ట్ చేసేనా?
స్టార్ట్ చేయండి మీరు.
ఓకే ఓకే. నాకు ఎంత టైం ఉంది? హౌ మచ్ టైం?
సార్ 1.5 hour తీసుకొచ్చారు హ్యాపీగా మీరు.
Okay, okay, fine. No issue then. I'll try to finish it by 1 hour. Okay. Okay. So what we will do is that we'll try to make up this lecture for 50 minutes, and then 10 minutes we'll have a discussion, and you can ask me some questions and all. Okay. Okay. Fine. So yesterday we were discussing few motivating factors about due to the proliferation of huge data, we call what is like how much (1948) Human Declaration Act. In that United Nations Declaration Act, it was decided that this privacy is a like fundamental right of every human being in this world. And people think that privacy means for some people it is seclusion. It means that they wanted to be left alone. Give me some privacy, like that you say, right? I can sense some bit of disturbance in the from your side. If you mute
Sir,
it,
no problem, sir.
I can sense some disturbance. Now it is okay. Fine. Okay.
So please
Yeah,
continue.
yeah. So some people think that privacy means it is seclusion. Some people think that it is the property. Okay, the desire to be paid for one's data. It means that it is my private data, and like everybody cannot have it. And some people think that it's my it's my privacy, or they feel that it is their autonomy. It means that they can do anything they like it. Okay, but one of the editors of a privacy journal, chief editors of a privacy journal, states that protection from being brought to the attention of others is privacy. And what what I feel is like privacy preserving is the ability to control the dissemination and use of one's personal information. So this lecture basically focuses on this point, the control and dissemination of use of one's personal data. See, like for example, now we try to understand that uh, if I give my phone number, and if the phone number is available with one of you, and tomorrow somebody asks, your colleague may be there, they may ask my phone number. Can you give me sir's phone number? So I wanted to talk. See, I have given you my phone number because I trust you, but I cannot trust this next person. Okay, and this is what we say, that this is that number, my mobile number or my sensitive information is my private property, right? That is my private thing, and it cannot be, I don't know, like you give the phone number to somebody else, and then later how the phone number may be used. So that's why I feel that like the control and dissemination of the use of my personal information, right? So if I generally, like what we do is if you have some phone number, and if somebody asks that, do you have that phone number, I want that phone number, you generally immediately send it and all. But if you have really that much trust, then only you have to give it. Otherwise, generally what is to be done is like you have to inform to that person that so and so person is requesting your call number. Can I pass this information? If they say yes, then only you should give that phone number to others. Otherwise, you should not give any sensitive information. Okay, any sensitive information. Suppose it's by trust. Somebody says that, okay, for example, I am having so and so problem, or some personal things and all you discuss with others. You are not supposed to discuss or take it forward to somebody else. It's the personal sensitive information. It should be controlledly disseminated. Okay. Now, what, see, some people think that this anyway, this security and privacy, all these things are same. As such, we feel about those things and all. Let us understand that what is the difference between privacy and security. Before this one, let me give you a small analogy. Like see, suppose today night you are sleeping at your home, close the doors, everything and all, and suddenly the armed force enter your house, banging your door, means they break open your door and they enter inside, and they said that some we got an information that some this some terrorist is available, or some an Naxalite is being staying in your house inside. So now here you just understand that if they break open your door, then it means that they are invading your privacy. If they do not break open your door, assume that that person, really a terrorist or somebody, a non-social element is available in your house. Okay, somebody is coming and threatening you or something doing and all. Okay, so it means that it's both are two different aspects. You understand now where is what is security and what is privacy. Privacy, if you see here, they have, the armed forces have invaded your privacy for the sake of security. But if you say that, okay, I don't want anybody to enter my house without my permission, it means that to attain privacy, to maintain privacy, the security may be at risk. Okay, see, these are different aspects when we keep on discussing this one. So general conventional security and all, if you understand what are the things that are involved, things like hacking, right? Somebody without permission and all, they take away your data. Okay, and some access control mechanisms are there to control some things are there, like theft of disk or theft of data or as such things may be there. and we do not encourage foul play. And generally to even while communicating, or like we while storing the data, we do the things in terms of using some encryption algorithms, right? So these are the things that we generally involve in privacy, or we deploy them in terms of security, sorry. But now the thing is that, what if the attacker use legitimate methods to steal your data? Now, the thing is here, let me go through here. Can she infer the data I wanted to keep private? Or how can I keep the data private while publishing some useful information? Today, if you see, it is compulsory, it is mandatory that data has to be disseminated to outside also. Suppose you take it the colleges like yours and all, or any universities or deemed universities or anything, or autonomous institutes as such, it is a mandatory that, as per mandatory disclosures, few things we have to disclose it. Okay, even the government data and all, it is mandatory that we have to disclose it. But to what level we have to disclose? How can I keep some data private while publishing useful information? The data that I publish outside should be useful, but it should be also that private data should be hold. So if we do this one, we call that one as an optimization problem. It becomes an optimization problem. And I publish my data, and somebody infer the data that I wanted to keep private. If this is the problem arises, then it becomes a decision problem. So I hope you understand that whether it is a decision problem or whether it is an optimization problem. Okay, in privacy. Next is like few samples if I give you. Alice is owner of person specific data, for example, public health agency, telecom provider, financial organization, like that. The person specific data contains what few things like attribute values which can uniquely identify an individual. Okay. So this thing, suppose I say that things like zip code, gender and date of birth, and or name, and SSN, social security number, Aadhaar number, let us call it that one. The sensitive information corresponding to individuals' medical condition, salary, location, all these details and all, right? These are person specific data. And today there is a great demand for sharing person specific data. I told you that people want to take sensitive data. They want your sensitive data. Okay, it can be, your sensitive data can be sold in the market. Everybody's. Don't think that what I am, who am I am just a student or I'm just a faculty somewhere. What does it matter to any? But it matters. Okay, so Alice want to publish this person specific data such that information remains practically useful and identity of the individual cannot be determined. So this becomes an optimization problem here, right? Now, see one motivating example if I see here. Suppose that Alice want to publish hospital data while the corresponding between name and disease stays private. Some people, what they do is that I'll just remove the name and disease. So this is the sensitive information, right? Let me remove this part and let me keep this non-sensitive data. Okay, like a zip code is there, age is there, and then the nationality is there. So from here, what others can do? Somebody may feel like that. Huh? Now, what if a attacker, okay, the attacker may have some knowledge, he may take it from the voters registration list, that so and so person, so and so zip code, and then so and so age and the nationality. Okay, based on this one, if he applies little bit of set inferences and all, he can say that, see, Bob, see, 136,067,29 US, 136,07, 130,67,29 US. See here and here, uniquely this matches. It means that his name is Bob, his name is Bob, and the disease, sensitive information disease he is having is heart disease. This is data leakage. This is a privacy breach has happened. A privacy breach has happened. Again, let me clarify you that there is a difference between privacy and security, right? This is a privacy breach that has happened. Now, what is this sensitive data? Okay, or like what we call it as quasi identifiers. So there are some fields which can determine other field. Like for example, I come to your institute and ask that, okay, I wanted to speak with Raju. Now you tell me how many Rajus are there. Okay, how I wanted to come and speak with, for example, some other name, Srinivas. How many Srinivas may be there in your complete college? I hope you are getting me. But if I wanted to say that I wanted to speak with 2106544, or if I say that fourth year Srinivas, okay, ID number this one, if I tell, okay, then definitely uniquely identify, right? So what I wanted to say here is that few attributes are used to determine other attributes uniquely. So there are some fields that may uniquely identify some individuals, right? So for example, zip code, age, and nationality. This is one example, okay, that has happened. Okay, with this one, the sensitive information, if this one can be, this one can derive the sensitive information, then we call those set of identifiers as quasi identifier. So the attacker can use them to join with other sources and identify the individuals. Okay, now this is simply a definition of a relation only. Okay, quasi identifier, what I have told, a mathematical definition only that I have given here. Now you see in 1997, this lady Sweeney, Latanya Sweeney, is one of the pioneers in that, in this domain actually. Okay, she got the medical data, she got the diagnosis, then ethnicity, medical condition, and procedure, total charge that was, and what are the visit dates, along with the date of birth, then the sex, and then zip. So with this data, she has mapped with the voters list, and then she was able to identify almost 80% of US population. 80% of US population uniquely. This was a privacy breach, right? This was a privacy breach. It should have not been done like that. So it can be done like that. She is a professor in Stanford University, and she was able to identify. So she told that the problem of privacy. So you know that why many countries and all, if you see like in Japan, in US, UK, and all, in Australia also, many countries, uh, they value their privacy a lot actually. So it means, what I mean to say is that privacy means different things to different people here. So if somebody, if you go to shopping mall, they will tell that, if behind they will keep a form and a movie ticket. For example, you take a movie ticket or bus ticket or any ticket in a shopping mall, and then they will tell that you write your address and phone number and everything and drop it in the box. You may get a lucky draw, and then you will get something. Okay, a prize may be there. There may be a possibility of a lucky draw. So what do you think? Anyway, we are not spending even 1 rupee. Okay, let me write my address, my phone number, everything, and then drop it here, and then I will go away. But you know, hundreds and thousands of people do that one. It means that thousands of records are being collected illegally. And after all, whether they will give a price or not, that is God knows. They may tell that you may get at the end of the day or at the end of the week a gift hamper, maybe like a 500 rupees, what is a steam cooker, may be given to somebody by luck, if somebody really get it, that one. Okay, they may get, they may not get, or as such. But how many records they are collecting, you just see in a shopping mall, like, and especially shopping malls in places like India and all. Okay, you see that how many people are entering into a shopping mall in a day, and out of that one, if 50% of them do also that one, you just imagine that how many thousands of records they get in a single day like that, right? So you have to understand, privacy is very much concerned. That's why yesterday I was telling you all time and again, okay, do not keep your photos, do not keep your sensitive information. Your face is a sensitive information. Okay, your biometric traits are sensitive information, your relationships are sensitive information. Okay, who are your friends, why do you tag them, all those things and all. Okay, so all the sensitive information the social network is collecting. Tomorrow it may be used for it may be misused. If it is used for the right purpose, it is well and good. Okay, but if it is used for a wrong purpose, okay, you it is, I leave this thought to you, beyond your imagination. Okay, to your imagination I leave it. Now, so what is the problem? Now let's come slowly enter into the problem, how to solve that problem to some extent while publishing the data into the website or any other dissemination mechanisms. Okay, so I have a database now. This database I wanted to convert to a anonymized database. Okay, D dash. This D I wanted to convert into D dash using some anonymization function. Okay, so if you see here, uh, the anonymization function from D should be converted to D dash, subjected to these conditions. Maximum similarity should be there between D and D dash. Okay, similarity mapping should be there with a high, on a high quantity. Then the information loss to be done from D to D dash should be as low as possible. And the quasi identifiers, what we told in the last slide, stating that those attributes which are able to infer the sensitive information are known as these quasi identifiers. Okay, these quasi identifiers should follow the domain generalization hierarchy. What is this domain generalization hierarchy? Okay, and these are the definitions and all. Let me see this. I'll tell you domain generalization hierarchy first. Okay, let me okay, this is domain generalization hierarchy. For example, you see that male and female both are population, so I keep it represent this one as a star. And for example, age between 0 to 25, I represent this one as less than equal to 25, and greater that one, greater than 26 to 50, I represent as, so this is the lower limit, this is the upper limit. Okay, so greater than 25, so I keep it 25 as a threshold here, right? Now here, then this and this combine to make it as a, again I represent with some other value. Okay, some other generalized. What I wanted to say here is that, for example, okay, all, for example, you have a tree which says that okay, there are like a student can be, it can be BTech student, it can be MTech student, it can be PhD student or MBA student or like that student. Okay, there are next level, if you go to, it can be any degree taking student. Then again, if you see in the BTech, you can say that they may belong to branch one, which is CSC, CE, IML, DS, or civil or something like that. Again, in CS, if you see, for example, they may belong to first year, second year, third year, fourth year, like that, right? Again, in that year, if you see, they may belong to section 1, section 2, section 3, if more members are there. In institutes like very big institutes like VIT, SRM, okay, who consume almost 10,000, 20,000 in a single year, okay, like that. So there may be very huge, so many number of CSC students may be there, and they will have sections also like that, or they may have again campuses also, different campuses also like that, right? So if you see, this is domain generalization hierarchy. A hierarchy is maintained, student, but what student? Okay, whether he is a second year C section student of a second year of EC branch from BTech. Okay, you understood that we can represent like that. Okay, so now let's go back here. And so it has to follow, quasi identifier should have this domain generalization hierarchy should be followed. Okay. Hmm. Now, so domain generalization, when I say this is what I told is this meaning only. Okay, given an attribute A, so I don't want you to go into these mathematical aspects and representation only. This is simply a representation activity only. Okay, so loss, I told that the information loss should be very less. So if you consider VG is the number of domain values that are the descendants of VG for that particular value, generalized value, then DA is the number of domain values in that attribute A of VG. Then WI is the positive constant specifying the penalty weight of attribute AJ of that particular. So what you need to do is that first you have to find out the loss of a particular cell, okay, of that particular cell value. Then that record value, okay, record loss for a cell, for a record, and for a table, complete table. Okay, a table comprises of multiple rows and all, right, this one. So this thing with respect to cell level or domain level, with respect to record level, with respect to table level, we have to maintain that loss, minimum information loss. That is what we told, right? Minimum loss, I loss, information loss. Okay, now let's go here. So people, some strategies have been given earlier, stating that a table T should satisfy K anonymity if for every tuple T that belongs to T, there exist K minus 1 other tuples. So what I wanted to tell you here is that, suppose now, if there is only one Srinivas in the class, hey Srinivas, I can tell that Srinivas, okay, uniquely I can identify. Assume that there are three Srinivas, K Srinivas. I wanted to say that K Srinivas. K is 3, K equal to 3 here. So K Srinivas, if it is there, uniquely I cannot identify that one, right? Uniquely I cannot identify who is that person, uniquely. Suppose a new person, as a new person I come to your class, I will not be able to identify who is K Srinivas. Okay, so a table T should satisfy, it says that a table T should have, for example, K is 3 anonymity if every tuple means, I hope you understand that, record. If every record in the table has 3 minus 1, it means that 2 more other tuples, right? So it is 3 anonymity, we call it as. What strategies generally we use for anonymizing? Generalization and suppression are the anonymization operations that are used in achieving K anonymity. Let's see here. What is generalization? You see, less than 40. For the age, we use this general. Replace the value with a less specific but semantically consistent value. So less than 40. Okay, just I am putting here less than 40. Suppression means nationality. I am not revealing any of the identity. Okay, whether he is an Indian, he is from US, from UK, okay, anywhere. I'm just putting it star, 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 representing with any symbol. Do not release the value at all, but you represent that one with some particular symbol. I hope you understand what is this generalization and what is this suppression. Okay, now you see original data. For example, we are having, this is the original data. Okay, now you see this data has been converted to this. You see here gender, we are suppressing that one completely here, and zip code, 2 digits, we are suppressing it completely. Okay, 816, here you see 816. Okay, and this 34 less than 50, we kept it less than 50. 45 less than 50, 66 greater than or equal to 50. Okay, 70 greater than or equal to 50. So if you understand here like this is too anonymized. It means that there are 2 tuples, at least 2 tuples. It can be 3 or 4 also, but there is at least all the tables, means all the rows should have at least 2 rows which are similar in nature. Okay, see here you see less than 50, less than 50. This is greater than equal to 50, greater than equal to 50. There is also another greater than equal to 50. This is less than 50, this is less than 50. See, you see here. Okay, these values and these 2 match, these 3 match, right, and these 2 match. So here you cannot tell this one as only one record is having 3 tuples, but remaining all tuples are having at least 2 equivalent, right? So that's why we call this one as 2 anonymized. Now, for example, this is the original table. Again, we anonymize this one into 2 anonymized table. Okay, now, so we say that we take, for example, this age, gender, and zip code. Okay, 3 attributes. And how many ways we can go on generalization like this? For example, 0 original value, suppose you give it here, original value, this is also original value, this is also original value, all the zip code 6 digits, right? In India, if you take it, 6 digits are there. Now there is a proposal to increase to 10 digits and all, right? Okay, so we call this one as level 0. Suppose you anonymize this one, means little bit in a upper level domain, okay, little bit abstract. This is also abstract. And if you are just removing or suppressing one of the last digit zip code, it means that again you are making some abstract. For this you are making some abstract, again zip code like that, 6 digits are there, 6 times you can keep on suppressing and all, right? Now if you see what are the combinations, which combination I can use such that I get, what is that I was been telling, maximum similarity, minimum information loss, and I follow the domain generalization hierarchy. Okay, that is my interest here. So if you see here, 0 0 0 level I can take it, or 0 0 1 I can take it, 0 0 2 0 0 3 0 0 4 0 0 5 0 0 6 I can take it, or 0 1 0 0 1 2 0 1 3 0 1 4 0 1 5 0 1 6 I can take it, or 1 0 0 1 0 1 1 0 2 1 0 3 1 0 4 1 0 5 1 0 6 I can take it, and 1 1 0 1 1 2 1 1 3 1 1 4 1 1 5 1 1 6 I can take it, or here you take it 2 2 0 0 2 0 1 2 0 2 2 0 3 2 0 4 2 0 5 2 0 6 I can take it, or 2 1 0 2 1 1 2 1 2 2 1 3 2 1 4 2 1 5 2 1 6 I can take it, right? So I can, it means that this many combinations are there. Now this thing, if I can I represent this one in terms of a lattice? Yes. Now you see here, this is 0 0 0. Now if I turn that bit, one of the last bit I turn it, then 0 0 1. Okay, or you can keep on like this, 0 0 1 0 0 2 0 0 3 0 0 4 0 0 5 0 0 6 I can do it, right? Otherwise 0 1 0 0 1 1 0 1 2 0 1 3 0 1 4 0 1 5 0 1 6 I can make it, right? Or 0 1 1, right? 0 1 sorry, 0 1 0 1 0 0 1 0 0 1 1, then again 0 1 1, from here again 0 1 2 0 1 3 0 1 4 0 1 5 0 1 6, sorry, where is this 0 1 6 zeros only we have to traverse like this, okay? 0 0 0 0 1 0 0 1 1 0 1 2 0 1 3 0 1 4 0 1 5 0 1 6. Okay, so I can traverse like this, right? I can traverse like this, and this one is a, now the thing is that this becomes a big lattice, or in conventional artificial intelligence, when we see this one, these type of problems we call it as hill climbing problems, right? Hill climbing problems. And this hill climbing problem, if you see, you have to settle, you have to go into some, find out some node, or somehow find out some place which is the optimum one. So we may have a local optimum, we may have a global optimum. Our interest is to go for the global optimum, right? The global optimum. So it becomes an what is this? Optimization problem. So you discuss, that's why there are some such techniques and all what you use conventionally in for the hill climbing algorithms and all, A star algorithm, AO star algorithm, such type of algorithms and all you will be seeing onto this one, right? So we will not use such type of algorithms here, but we use some, for example, we use some heuristics and all. Now you see here, so let me tell you again, give a little bit of description about this one. So an arrow denotes that a state is direct generalization. It means that from here to here there is a direct generalization, from here to here there is an arrow like this, right? So there is an arrow like this, so there is a generalization like this. Okay, you can go on like that. So there is a generalization. The state with minimal generalization 0 0 is the bottom and represents the original input, right? This is the original input 0 0 0. If you see here 0 0 0 level, it means that all original data is there. And if you see the highest levels, that will be, it means that everything data is suppressed here. It means that there is a complete information loss, right? The state with the maximal generalization is 216 at the top. Here if you see 216 at the top level, level 10. Then the state which has been applied to anonymize the data set in the previous example is 113. So if you see here, this one is 113. This is less than 25 or greater than 25 you are given. Then this is also 1 1, and this is 3, I think, right? 1 1, yeah, 113, right? 3 digits have been suppressed. So this is, I hope you understand this one. If you see this one, if you publish this value, If you publish this value, then complete information you are publishing it. If you publish this value, it means that complete information you are suppressing it. You are means there is no use of publishing this one, this value. But you see, understand here, if you publish this value, you are completely giving privacy. If you are publishing, but there is no utility. If you are publishing this one, you are giving complete utility of the data is there, but no privacy is there. So we have to settle somewhere in these nodes where, okay, where we can optimize something. So there should be data should be published, but some optimization, and we have to attain privacy levels. We have to attain some privacy levels of k anonymity. Okay, we should be able to get that k anonymity, but we have to balance this factor of uh, like utility and privacy. Okay, now, so if you see the lattice, if you take it the size, this is formula given. Okay, what is the size of the full domain generalization hierarchy? So the thing is here, the challenge is, if you see here, how to traverse the lattice to find the optimal node. So it becomes a utility versus privacy problem. Does the traversal algorithm has a balance with the time, information loss, and k anonymity? And is this method sufficient to ensure privacy? And how to ensure privacy of dynamic structures? Okay, for example, social network analysis and all such type of things. Yesterday we have seen Obama's privacy breach, that one video and all, right? Yeah. So if you see here, okay, first of its kind algorithm was given by, again, that Stanford professor Sweeney's algorithm. Okay, Datafly was a name of that algorithm which she has given. Datafly uses a greedy algorithm to search the domain generalization hierarchy. What it does is that at every step, it chooses a random move upwards the hierarchy. It means that from this table, randomly one of these three, it just moves like this, like this, like this, and it keeps on checking for privacy. Means check, it moves like this. It checks randomly one or two or three, anywhere you can go, and then this node, for example, it is moving to this node, then it will check for that k anonymity. If it is not attained, then randomly you move forward again and check whether that node achieves privacy or not, like that, and moves on like that. Okay, this is what we call it as uh, like at every step it chooses a random move upwards and upwards the hierarchy. If k anonymity is satisfied, then it terminates there, it stops at that node. But one of the drawback, if you see, with the Datafly's approach is common with all this type of this hill climbing algorithms, is that it may become trapped in a local optimum. Possibility that the information loss will be huge. There is a possibility information loss will be huge. Next one is another person, Pairangala Samarati from Italy. Okay, she has given one algorithm. What she tells is that Samarati's algorithm is based on the axiom that at the highest level, like if it satisfies domain generalization hierarchy, then the levels of height greater than h also satisfy k anonymity. Okay, so if what she mean to say is that, assume that in a particular level, suppose here the k anonymity is satisfied. Okay, here the k anonymity is satisfied. Okay, it means that higher level everything the k anonymity also satisfies. Upper level, okay, from here all the upper levels will satisfy the k anonymity. And here suppose it not satisfy, means down there may be a chance where like again you need to go down. Okay, so here what she simply says is that, based on that axiom, that if a node at level h at a particular level in domain generalization hierarchy satisfies k anonymity, then all the levels of height greater than h also satisfies k anonymity, right? So it means that at a particular level you check for k anonymity, you are not achieving, go one level up. Okay, or some levels up and then you check, then otherwise some levels up and then check, like that. So how to go, she uses a heuristic called as binary search. She simply uses binary search only. Use a binary search over the levels of domain generalization hierarchy. For a domain generalization hierarchy of height h, for example, the search starts at level h by 2, half. from the middle of the lattice. And if that level satisfies the k anonymity, then it searches at the level h by 4. It means that it goes still upper. Okay. Otherwise, it searches at the level 3h by 4, and it goes on the same way till it finds the solution at the lowest possible level. Okay. This approach assumes the optimal level, global optimum, the one with the least generalization, and within that level, it takes the node that has the maximum or minimum information loss at the solution. So the drawback is that time consumption is a little bit higher than data flight. So what we came up of, this is our own algorithm only, okay? And this is one of my chapter. I told you that this is one of my chapter when I did PhD some 12 years back and all, okay? So that only I'm just giving you here. Um, and this thing, since all these things are attached with big data, okay? Why I thought that this is in terms of privacy when I speak it, for this big data aspects and all, it will be good because today the more the data, okay, more the inferences can be done, the better the AI algorithms are there available in the society. If you use it, then you can infer the best of the best. And if you are able to infer that one, it means that your privacy is breached. That's why, okay? So an improved greedy algorithm has been proposed here. So the algorithm starts by checking for k anonymity in the lowest level of the full domain generalization hierarchy, which has only one node, okay? The one least level. Now, if k anonymity is satisfied, then the data set is k anonymous as it is and needs no further anonymization, right? But if the k anonymity is not satisfied, then k anonymity is checked up, generalizing each attribute at a time. So each attribute should be done here, not randomly move forward, okay? Each attribute has to be done and then move forward. If none of the nodes satisfy the k anonymity, then what we have to do, then the node which has the highest anonymity is to be selected, taken into consideration. So in case of a tie, the node which has generalization and most differentiated attributes should be selected, and the k anonymity is checked by generalizing each attribute again at a time for the selected node. So the above steps are repeated. Now if you see here, uh, this thing, like for example, all the three algorithms in a single lattice, I'm giving it, for example, these are four attributes 0 0 0 0. Then as you move on, you have got this processing strategies are there, okay? If you see, this is data fly, okay? This arrow is data fly, just moving randomly, moving upwards. And these yellow lines, for example, first it will check from here, then it is not able to attain this one, then from this is the least and this is the highest, then it checks and goes on. If attained, then this one will be the highest level, and this one then again construct the binary 1 by 2 and then again come here and check at this level. If it is satisfied, okay, it will goes up. Otherwise it is not satisfied, then it will this one has the highest and this one has the lowest. And then what improved greedy does is that from this node it moves to the upper level, right? It moves through the upper level and then checks with each of these like it checks with each of the attributes, not randomly moving forward. The node which has the highest like a generalization, that we take into consideration, okay? And then check for all the attributes there. So this way we have done it. And let me tell you some graphs. Let me show you that, like if you see, this is like the anonymity, k anonymity you achieve, okay? At when 10 records, 10 anonymity, 20 anonymity, 30 anonymity. This is for, I think this is for cups data set, I think it sorry, adult data set. This is one data set available in UCI machine learning repository. From there only, okay? You see here, the bottom one is the data fly algorithm. This is Samarati's algorithm. Sorry, this is like improved. The green one is the improved greedy algorithm, what we have given. And this is the Samarati's algorithm. So time taken by Samarati algorithm is more compared with this both, okay? But you understand data fly take the least time. And if you see here, at what level the anonymity, the generalization has taken place, at what level? Okay, anonymity versus level of generalization. If you see here, the level of global optimum, if you see, Samaratis gives the best result. Samaratis algorithm, and data fly given gives the worst results compared with these three. And this improved greedy algorithm, if you see, it is almost at par with the Samaratis algorithm. So if you see here, information loss also, let us consider. Information loss is less almost, okay, to this Samaratis algorithm, and also improved greedy algorithm also. But information loss is more with respect to this data fly algorithm. With respect to time, execution time, data fly is good. With respect to level of generalization and information loss, Samaratis algorithm is good. But when I balance both, improved greedy algorithm is the best, right? It's balancing. So now the thing is that, again, with this k anonymity also, there are some problems are there. What problems are there? You see here. Now, for example, I take it this as one of the table, and if you see, all the information here are cancer, 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 cancer. It means that this we call it as homogeneity attack. Okay. Now, uh, this is for anonymous data, right? You take it, and these things, if you see that one in a cell, everybody are, it is equivalent only, no doubt in this one. This is k anonymous, this is for anonymous. But if you see in the sensitive data part, it is same value is there. So it means that this may be having a homogeneity attack. So k anonymity suffers from the following attacks. One is the homogeneity attack. Next one is the background knowledge attack. Okay. So what is this background knowledge attack? For example, here only two diseases are there: heart disease and viral infection. Okay. So assume that from a particular area, okay, you take it, for example, the Nepal area and all. For example, in the Nepal area and all, there is a very less possibility that, because people keep on trekking onto the mountains and all, there is a low probability that somebody may have a heart disease. So it means that what is the other disease that they may have? It is the viral infection. So it means that here, what I mean to say is that if the attacker has the background information, with that background information also, he can attack this particular table. Okay, this particular equivalence class, we call this one as one of the equivalence class. Okay. Now, so the method proposed is also there should be at least L diverse. It means that in each of these field, sensitive field, there should be diverse, diversified sensitive values should be there. How many diverse? It should be L diverse. It may be 2 diverse, it may be 3 diverse, it may be 4 diverse, but there should be diversified. Okay. So an equivalence class is L diverse if at least L diversified values of the sensitive attribute is there. And if all the equivalence class has the diversification, then you call that one, the table is also L diverse. Okay. Now, for example, you take this, okay, a small example. This is the zip code, age, and salary. Again, the disease is there. If you see the diverse, if you see here, stomach cancer, pneumonia, bronchitis. Then this bronchitis, flu, and gastritis. Stomach cancer, gastritis, and gastric ulcer. These are three diverse. Okay, this is a three diverse table, right? In the sensitive information, there are at least three diverse values here. I hope you're getting me. Yes. Now, again, L diversity suffers from some attacks. What type of attacks are there? Similarity attacks and skewness attacks. What is the similarity attacks and skewness attack? For example, you see gastritis, then uh, you have gastritis and stomach cancer. All these are stomach related. Similar types of, means similar organ diseases, or related to similar system may be there. And also there is a possibility that skewness may be there, means some data may not be available, that diversified data may not be available. Then how can you put this one? See, for example, in a rainy season or in a particular zone and all, if you go and see that, especially the mountain areas and all, majority of the cases, what do they do it? It is like some viral fever or some dysentery or something. So where is the diverse there available? Viral fever, viral fever, viral fever. Everybody are having viral fever during corona time and all. You just understand that everybody, whoever is suffering from whatever may be, corona, 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 corona is that one. Skewness. The data that you get is skewness. skewed. Data is completely skewed. How can you make it diversified again for that one? Whether corona in the nose, corona in the mouth, corona in the stomach, corona in the skin. How are you going to identify that one? It is difficult, right? That is skewness. Sorry, the yes, that is skewness attack. Okay, so to overcome that one, a method was proposed: T closeness. What is this T closeness? Let us understand this as privacy is measured by the information gain of an observer. Okay, right? How much information is gained by an observer? For example, information gain means what is the new information that is gained by that particular observer. For example, I say that, let me give you a small example. Okay, uh, a snake, sorry, a dog bit a man. A dog bit a man. Fine. So we understand generally, okay, the new information here that you gained is that, ayo papam, somebody was bitten by a dog. Okay, he bites, the dog bit a man. Okay, fine. Now assume that the inverse is there here. It means that a man bites a dog. A man bites a dog. Now you just, this is a new information for you, right? This is something, yes, okay, but this has never happened before, and something new you are getting, new information you are getting. A man bit a dog has more information combined compared to a dog bit a man. Dog bit a man, generally you know that, okay, if you annoy a dog might have bitten that man. Okay, fine. But that is a new information you got, but the new information which is very, very less compared to a man bites a dog now. Okay, that is the new information that you are getting it, right? So before seeing the released table, and the observer has a prior belief about the sensitive attribute values, and after seeing the released table, the observer has a posterior belief. Now the information gain, what do we say? Posterior belief minus prior belief. So an equivalence should be so close enough, okay, between this posterior belief and then prior belief, right? Posterior and prior belief, it should be so close. T close, we call that one as a T close. It should be close enough. It means that in an equivalence class, I told you that in a table, one particular set, if you take it, that is an equivalence class. That equivalence class closeness should be less than or equal to T, a measure called T, T closeness, 0 0.1, 0 0.2, 0 0.3 closeness should be there. Similarly, all the tables, okay, an equivalence class is said to have T closeness if the distance between the distribution of a, it is regarding the distribution of the sensitive attributes in that class, and the distribution of the sensitive attributes in the whole table is no more than a threshold called T. A table is said to have T closeness if all equivalence class have got is T closeness. Okay, this is what we call it as T closeness. So I'm not giving much example and all. You can go and investigate more onto these aspects of T closeness and all. OL diversity, T closeness, all those things, and advanced mechanisms also. You can go. You can go to some of the uh, leading journals and conference articles, and then you can see it onto that one. Okay, now how, suppose you devise a privacy preserving algorithm, how do you decide that? Okay, that evaluation of the privacy preserving algorithm, how do you do it? So first thing is that performance, the time needed by the algorithm to hide a specific set of the sensitivity information. How much time? See, for example, if it is computationally intensive, by the time you compute to make it into a, turn it to a anonymized data set, if the data set is already leaked and then into the market, it means that there is no value. It is same like when I ask you for a pen. Suppose I am writing very speedily, and I am writing some notes or something, and I ask you for a pen. And if you don't give me at the right moment, you tell that tomorrow I'll bring a pen for you. What is the necessity that tomorrow can't I bring it? So the help that you render, the help that you give, if you don't give it in time, then there is no necessity. So the time needed by the algorithm to hide a specific data set of the sensitive information. So it means that the performance of the algorithm that is used for anonymization should be good enough. And the utility of the data after preserving the data, there should be some utility of the data. Otherwise, you just suppress everything, then the highest level of generalization you get it, of the domain generalization, there is zero utility of that one. Then the level of uncertainty. So the uncertainty level with which the sensitive information that have been hidden can still be predicted. So it should be, there should be more of fuzziness. So uncertainty should be very high there. And resistance. It means that those algorithms should be resistant, that attackers are using some AI or data mining algorithms and all. It should not be able to attack. Okay, this is what is the privacy preserving this one. And risk with artificial intelligence, if you see, comes with people using artificial intelligence. The Jeffrey Hinton, the Nobel Prize winner in physics in 2024, he was the person who has invented these neural networks, all these things and all. Okay, sorry, this majority of the neural networks contribution, okay, in the neural networks domain is given by this Jeffrey Hinton, though he was not the main inventor of the neural networks. Okay, so if you see here, risk that come from the people misusing AI, or risk that come from AI becomes super smart and deciding it doesn't need us. Now, with this, like you have got a short-term risk with AI, and there are long-term risk. With respect to, I am telling that with respect to the huge amount of data, okay, and you have today the AI as the booming factor. Where are the problems? Okay, you see here, the short-term risks are very important and should be addressed urgently, mainly to do with people misusing the AI. Job insecurity is there, fake videos, cyber attacks are there, designing new viruses are there, and usage of trained weights and all, like the deep seek and all, what it is doing, right? It has used somebody else weights trained. That is what is the claim by some, the chat GPT and all, right? So they used our weights and then they are doing the activity and all. And another one is long-term risk. What we make things more intelligent, are we making the things more intelligent than ourselves? The question is, what's going to happen when we have created beings that are more intelligent than us? Computer systems are programmed to tell a neural network like what the system has to do. We have to tell it, but now the system will tell us what it has to do it. So let me play a video for all of you. Okay, I hope it is your sound. Please adjust your sounds and all everything. I'm just playing a video for all of you. So warning here is that if you don't learn to use AI, AI will learn to use you. Master AI or be mastered by AI. Learn how to use AI in your job, or AI will take away your job. I hope this is eye-opening for all of you, all of us, in fact. Okay, you just imagine that. This is, of course, okay. Let me stop here and then take some questions from all of you, please. Yeah, I'm open for some questions, please. No questions? Any questions from anybody? Even people who are in YouTube live and all, you can just post the questions to the coordinators. They will type it here for me. At least you can message me if any questions are there or not.